become available on the 3DPMolds website, YouTube, wherever else you access your video content. So while we wait for everybody else to join in, it's good to see you all. I've been looking forward to this. Today's topic is one that is very highly relevant in the situation that the world is finding itself in today. I think we can all agree that the last handful of years have been challenging, but we are seeing a lot of supply chain challenges resurfacing as a result of recent politics. So I've been looking forward to looking at one of those key applications where you can start talking about not only development and low volume manufacturing, but where you can also start talking about increasing the volume that is manufactured. And SK Industriemodell, of course, is one of the leading players, if not the leading player in this field. So it's 2 past now, and that means that I will slowly get started. My name is Lasse Ståhl. I founded 3DPMolds a little more than 3 months ago now, coming out of Next 3D. Before that, I was affiliated with Adifab. And I've been deeply involved with the 3D printed molding industry for almost a decade now. As I was talking about, and just recapping what I think everybody knows, the world is in a state of flux these days. A handful of years ago, we had the COVID-19. We had a large ship blocking the Suez Canal. Then we have and still have Ukraine. Now we are slapped with tariffs in a situation where people are kindly realigning world trade patterns. And that means that for manufacturers, for product developers, for everybody associated with the noble art of manufacturing stuff, supply chain management, development of new products is becoming increasingly a question about having the right agility, the right scalability, the right flexibility, because you don't really know what will happen tomorrow, and you need to be ready to respond fast as things change. 3DPMolds was actually founded as a company that is dedicated to shortening development cycles, increasing supply chain resilience. As you've probably noticed, I'm a great fan of 3D printed molds in general, and part of what I see as the important contribution of this technology is that it allows us to combine the best from 3D printing with the best of injection molding, without really forcing a lot of compromises. Of course, you need to know your way around the technology. And for that reason, one of my key goals in this life is to connect companies with manufacturing partners, like for instance, SK Industriemodell, who know how to apply 3D printed molds on a very, very high level. Of course, I also help people wanting to implement 3D printed molds in their own operations, but that's a topic for another discussion. At this webinar, we will be recording, as I mentioned in the beginning. We'll also be making the slides available for you guys, so you don't need to start copying the screen or anything else. In order to ensure that Sebastian can keep their flow, we will be taking questions in the chat. I'll note them down, and then we can get to them in the end. And of course, I like to keep you updated on everything that's going on. So I'll be circulating the slides after this webinar, and I'll be circulating an invitation to sign up for our newsletter. I think enough about me, enough about 3DPMolds. I'd like to hand over the scene to Sebastian Krell and Sebastian Müller and SK Industriemodell. So here you go, guys.
Okay, thank you, Lasse. So first of all, I'd just like to introduce myself. My name is Sebastian Krell. I'm the managing director and owner of SK Industriemodell, and today I'm here with me is our project leader for printing molds, Sebastian Müller. Just a short brief about the company. We currently have 20 employees, cover a production area of 2,000 square meters. We run 9 to 10 different injection molding machines in different sizes, from 40 tons until 200 tons of clamping force. And we have our own tool shop where we mainly build aluminum and steel molds. And then we have 6 CNC milling machines. We have been working on a lot of different research projects, also with the Aachen University, and actually our competencies in printed mold inserts results from 2 research projects we did with the Aachen University. The first one started over 8 years ago. So if you can move to the next slide, Lessa.
Yes.
Okay, so our main topic today are the 3D printed mold inserts that we use in different variations. Just to give you a rough overview, what we did last year is that we printed over 1,000 of these inserts for different kinds of applications. Some of them we only printed 2 or 3, 4 versions. Some of them we printed up to 50 or even 100 different, 100 of the same insert, but for different applications. So first thing that you can do with the printed inserts is that we dissolve the complete cavity. And we have the example here, and we will be showing that later on as well. You can probably see it better in the picture, is that we print the core cavity. What you see on the outside are lines for venting. That's why we also have the part with the vents, because what we're doing is we have no way for the air to get out. We need venting channels on the part in order for the air to get out of the cavity. And it's also, even though we dissolve the mold after we inject it, so it's a lost mold, we always use a split mold that also helps us with venting, but it also helps us to clean the cavity from uncured resin after the printing job. The second option that we have, and we will also be doing a live demo later on today, is our hybrid tool. With the hybrid tool, what we do here is we combine an aluminum tool with a 3D printed insert. So we had a customer, he identified an area where he wanted to do a couple of changes to the design and wasn't sure because of the material used how it should look like. So what we did here is we printed the inserts in the area where the part changed, and we kept the rest as an aluminum tool. That also allowed us to easily add ejectors to the tool, so we could basically have the tool run fully automated if we would insert the inserts by a robot. Right now, for the demo today, we're going to do that by hand, but technically it is possible to have that run fully automated. So with this technology of hybrid tooling, allows you to combine the best of printing, where you possibly have an undercut and you would need a side operation to eject the part, and you reuse the part, or you reuse the part of the tool where you use aluminum to have a more steady tool which will withstand a lot more shots. And what we're showing here is one example. We have done this hybrid tooling case in different kind of versions. So even bigger parts can easily be done like that. For example, what we have here also, I will show that later on, is a fan blade of the Vespa. These parts are rather big. What we can do here is we can dissolve the part where the blades are in, and we can reuse the other half. Now it's printed as well. If we would do more shots, we would just do that in aluminum.
Sebastian, I'm just going to pause you here. Do you need me to allow a video to be shown? Because right now I'm seeing the slides, and if you want to show a part, then I think we should.
Okay, we can do that later on. We'll do that later on when we're done.
Okay.
Okay.
Excellent.
We'll take the parts with us. And so there are different options there. For the hybrid tool, that is a very strong combination if you use it in the right way, where you can use the best technology for easy 2D contours of the part, and where it gets more complex, especially with undercuts, you can use a printed insert. In general, for the 3D printed mold inserts, we're very fast in printing them. We can, for the inserts that we use for the hybrid tool, so the small little clip inserts, we print 50 of them in 20 minutes. So we have a very fast availability of these inserts. You can use that for testing. And what is most important, you test with the serial material. So for any of you where the material is key to the success of the part, also, for example, medical applications, there it is key that you use the injection molding material as early as possible in prototyping. You can produce any kind of parts with metal inserts. You can use any kind of high performance materials as well. So in this printed material, we can also inject PEEK. Unfortunately, we were not allowed to show the last part that we just did in PEEK due to customer restrictions. So I hope you understand that. But we did inject a very small part that's about the size of the clip that is shown in the hybrid tool, and only the clip size. And we injected that in filled and unfilled PEEK. The material withstands that temperature for a short period of time. And with the right settings of injection molding, you can make that a success. You can also use the technology to validate potential design changes in an existing mold. So for example, you're running a serial mold, you have done thousands or 10,000s of shots, and for whatever reason, you need a design change. Before investing a lot of money into the tool change and stopping production, it might be an option that you validate that if you only need 2 or 3 parts to validate that with a 3D printed mold insert, and then move on with the tool change. Last up that I already told you before, a little bit about spare parts or what can you do in that region. Lasse has mentioned that in his first words. Things are getting more challenging all over the world, and the question is it wise to have spare parts, for example, for like really old machines, but you still want to service your customer, and you might only have demand of 5 or 10 or 20, maybe 100 parts per year, but maybe also at different locations in the world. So what you could do with this technology is you could validate the design of the printed mold. You can deploy that to different countries, to different plants that you're producing in, and they could actually print the mold, inject these 5 or 10 parts, and you could still have the spare parts in the injection molded material. There's no need for you to reevaluate if a printed part would do the job, because you have been doing injection molding for years on that part. You know which material to use, and you know which material will do the job from the injection molding standpoint. So that is a really good option to look at if you're going to very low volume spare part production. Okay, Lasse, can you move on? Okay, so yeah, so what else do we do? Of course, main topic for today are the printed mold inserts, but as I said, we do a lot of aluminum tools. Last year, we did around 350 aluminum tools. We did around 25 steel tools. We are very much linked with the Aachen University, where we do a lot of research projects. Currently, we're into 3 different research projects. We cover different areas there. So we cover the area of 3D printing, we cover the area of tooling. We also cover the area of injection molding with special materials or for special applications. So we have a very good understanding of that research field, and also offer research services to all of our customers. In injection molding, we focus on low volume and prototyping injection. We do that for spare parts. We also do 2K, 3K parts, so 2 plastic materials with metal inserts, all kinds of inserts, glass. Whatever you can think of, we do the overmolding that as a prototype or small volume production. We also work very closely with a lot of material suppliers in the injection molding side. That's why we have a wide range of experience in that field. So whenever it comes to the question what material to use for your application, we probably have someone that we can work on a good solution for you and your product. Okay, listen. And that was just a short overview of what 3D printed mold inserts are, what we as SK can do. And for those of you somewhere around in Germany, or if you're willing to travel, we do have the Cutino Fair next week. You can meet us at the booth there in the startup area, and we will be presenting the 3D printed mold inserts. You can have a look at that, and if you have any project idea you want to discuss in person, we will be there to help you.
Excellent. So did you wanted to show some parts to the audience? Because then I'll just mute the slides for a while so you can actually access the video.
Okay, so what we're just talking about was the Vespa fan wheel. So you can see that that's in size. That's like a diameter of around 100. These are the mold halves. This was printed. We injected that. Obviously, this mold, the part was that it's dissolved, so we printed an extra one for demo cases. The key challenge here was that we didn't want to waste too many molds and getting a good part. So we spent a lot of work up front to make sure that we could fill the cavity with the first shot. And after doing that, after finding the right settings for that, we gave it a try. This one worked out, and we did a few parts of that. The reason why we did this part with a printed mold was, as you can imagine, with all these blades, the tool is quite complex and quite time-consuming to produce. And our customer requested, he only requested 5 parts. So this was our way to go for this kind of technology. Gave us the opportunity to fulfill that, stay within a reasonable price range for the part, and we can redo that every year or every 2 years. Doesn't matter what the demand is, and nobody invested big into tooling for that. So this is a very strong case about spare parts and how you can also produce them locally if you want to. So if there's a worldwide demand of 30, you could produce 5 or 10 in any region of the world. You wouldn't have to be shipping that all over the world, and you would have local manufacturing of that. Another reason why the customer asked us to do that with a printed mold and to get a new version, there are versions of that part out on the market, but they're not in very high quality. So what we used here is a reinforced polyamide, and in this case we also use a recycled version of that, and which gives the part enough strength that it needs compared to the standard part that is in the market that's solely made of PP and lasts about half a year until it breaks. And with our part, we know that we can outstand that. That's why we do have a higher price, but there are customers that are willing to pay that price. So that's why our customer asked us to fulfill that need. The other thing that I just showed were the printed mold halves that we have here. This is why we always do a split tool, is so we can have the venting, a better options for the venting, and we have a better wash of the uncured cavity. So these were the also the ones you've seen in the picture. This is what the part looks like with the venting channel. So we have, on purpose, we have not removed them yet to give you a view of how this looks like. And yeah, we need to remove that, but this is something we can do if we only do a few parts. And these are the tiny little inserts, but you will see them shortly in the live demo as well.
And all those parts are on display at the Cutano next week, if I'm not mistaken.
Yes, correct.
Sounds great. So I think we could do one intermediary question before moving to the live. It's George asking, how many shots do you need on average to find the best setting parameters on the 3D printer and the injection molding machine?
That is a question. Well, I cannot directly answer that question because we need to set a few parameters. The first one is what are the tolerances that you're expecting? So the tighter the tolerances are that you're expecting, if, for example, you go up to TG5 or maybe on some areas even the better tolerance, we would need more iterations to do so. And so that's for the printing the mold. For the injection parameters, we now have a system where I think most of the time we need 1 to 2 shots until we can fill the mold. But as I said, we have printed over 1,000 molds last year. So we do have a wide range of experience in that area that we can learn from and that we use every time we do a new mold. So if you start off with that, probably you're going to use 5, 6 molds, maybe even more, to get a good filled part. This is a learning curve that you would need to implement on your own to make sure that you have a success with the first shots that you do. So we do spend quite some time up front to make sure that we can fill the part correctly without wasting too many molds, because this definitely is a challenge with the technology.
George is also asking about the average dissolution time. Can you comment on that based on your experience?
Well, again, also this depends on the parameters, but this could be really fast. So this part here that we showed, we printed the molds. The first version that we printed basically failed because we did a wrong assumption there. We have a very thin wall and we have an opening here in the side, and it's hard to, I will show you downstairs more. So then the next day we printed a new sets of molds. We injected that again. And then the day after we had some good parts. So there we had like a 3-day turnaround on that. To be honest, this is not something that we in general can offer because we have a lot of other ongoing projects. But if we have let's put it that way, if the cut data that we receive is a very good quality, it is easy for us to create a mold and then print the mold and inject the parts is the least time that we need. So it's really about the data quality that we receive before, which actually defines the time that we need. And then we can achieve a 1 week or 2 week turnaround without any problem.
Sounds like a great starting point. Perhaps, Sebastian, we should be moving to the live demo now.
Okay,
I guess you'll be.
let's go ahead and then we will take you to the machine and show you how this works.
Okay, so there'll be, I guess, a 1-minute break in the session. We'll rejoin next to an injection molding machine, right?
Okay, great.
Sounds good.
Okay.
So now we're standing next to the injection molding machine, and I guess you also do that as part of your service and support delivery.
So here we have the injection molding machine, so we're ready. We have everything set up. We will get a closer view of the mold and everything just in a while. So what we're using and what is very important to us is that we have a standard injection molding machine. So there's nothing special about the injection molding machine, but what we do here, we make sure that if we inject, of course, small parts, we also go on a smaller machine. But right now, what we have here is we have the hybrid tool. So we need a little bit of a bigger setup than we would usually have compared to if we would only have a lost cavity. So we're good to go. I can show you the inserts that we have. So we printed some of the inserts. This is the size of the insert, and this is the final part. So here we do have the part where we still have the printed insert, and the other one was formed by the aluminum cavity. What we can do with one part here is we prepare the bucket with hot water, and we can put the mold inside, and we will just wait a few minutes. In the meantime, we will do our demo, and we can take it back out afterwards, and I can show you how easy it is to demold these kind of parts. Okay. So we'll show you how everything works. I'll just give you an overview of the machine setup. So what we have here is we have our mold base. In the mold base, we have an aluminum frame with ejectors. And he will be inserting the printed insert now.
I hope you will see. So
it goes into the cavity. So here it is. And now we will do the first shot.
So we just close the door. Everything is okay. Starting the process.
I mean, now the boring part starts because you can't see anything what's inside the machine, but this is with the printed insert, we need a longer cooling time than if we would have a steel or aluminum insert. So right now the cooling time is set to 20 seconds, which for a small part like that is quite long, but this is what we need.
So now we're ready.
Yep. Okay, so we still got the screw attached. We have the ejector set, so we just lift the part out, and we can take it out manually to actually show you how it looks like. So this is the final part with the printed insert, and now we need to remove the sprue, and we would need to dissolve the insert, and the dissolving insert process is ongoing. In the meantime, we will just do a next shot. So again, now we insert by hand. This can also be done automatically if needed, but not for the demo case. So standard machine.
So if you're looking at an average manufacturing case and you're saying that you can produce 50 of those inserts in 20 minutes, that means that your printer is basically keeping up with the injection mold machine based on the cycle time.
Yes,
if you run it automatically.
Yes.
That's nifty.
So we have the part, cut off the sprue, and now we have the part. You can dissolve the insert. I put it into the hot water.
We'll also put that one in the hot water, just to give you an overview of how that will look like. Okay, so now just while we do the next shot, I will show you so you can have the comparison. This is the printed insert for the clip versus the tool that we printed for the Vespa fan blade. So this part actually is too big for the machine that we're using here for the insert. So we need to go on the bigger machine. And we also, and this is the advantage also of the resin that we're using versus ceramic filled resins, is that it does not break very easily. So it's a little soft touch. With that, what we can achieve for big parts like the Vespa fan wheel what we can do here is we can apply a lot of clamping force to the mold. So we injected that part with a clamping force of 50 tons. And that is needed to fill the part to get a success with the first shot. We absolutely need that setup. These are all values of experience that we have made over the last years, and that we know how to set up a tool like that.
But this also demonstrates, I think, in a very nice way, Sebastian, the versatility of 3D printed molds. You can do the small stuff, you can also do the much bigger stuff.
Get it easier out.
I want to just do one more part.
Mm.
Okay, as some of you might hear, we're running this tool on a fully electric machine. This is not 100% necessary for this kind of parts, but if we get into very complex parts, this is a huge advantage when trying to fill the printed mold cavity.
Was the last one.
Okay, so now we still have the parts in the hot water where we're trying to do, we softened the printed material. I'm going to take one part out now. I can show you as we have an open surface on one side. We should be, yeah, we're already able to take the mold off and we have the final parts. Now this is the mold insert I just broke open to demold the part. I need to clean this a little bit, but basically that was it on small parts like that. This can easily be done. See if the next part is ready as well. Yeah, this one is ready as well. I can just crack this open and you can see the steamed part. And here you can see the undercut. That's one of the reasons why we use the dissolvable or softening insert. Okay. Good.
Nice one.
We would be, if there are any, Lasse, if there are any direct questions in the chat while we're down at the machine, please let me know.
I think people just digesting what they saw, and I guess the key benefit of what we're seeing here is that you can dramatically simplify the design of your low volume tool, while at the same time dramatically increasing the reusability compared with if you do the standard 3D printed version. Is that more or less correctly observed?
Okay. So there are no questions?
Nope.
Okay.
Not at the present age.
Okay, then we will go back up. Just give us 30 seconds.
So now we are back.
Yes.
Wow, you're fast. So this entire setup is going to be on display at the container. Is that correct, Vincent?
Well, we won't have the machine running, but we have all the samples there. We have a video of basically what we just did. So but as all projects are unique, it does make sense. So if you have the chance and the need of a project, just have a chat with us in person so we can talk about the project, because all projects are different. And there's no guideline that your project with this technology will work. And I think one thing that is very important to understand is, although this is a really fancy, nice technology to use, it will not solve all of your problems, and not at once. So what we need to do is we need to look at what are your needs, what are your expectations, and then we can tell you, okay, how can we get there, and what is the benefit of doing it with this technology versus other technologies. And as we already showed with the hybrid tool, we also like to combine these technologies. So it might be that your project that you're looking into will have the need of an aluminum tool and printed inserts, or multiple combinations. We have done all kinds of things. We have done aluminum tools where we milled half of the tool, and then we had 10 different inserts that we printed. This is also an option. Other options are like to print the complete insert. There are different kinds of ways of doing it. So it is very important to have that discussion up front, to look at, what are your needs, what are the materials that you want to use. And the strengths definitely of the technologies are, we just had that case with a medical customer. He was looking into 5 different materials with 5 different shrinkage values. So that would have been 5 different molds to test the part. So what we could do there is we just printed 5 different inserts. And then he could compare, okay, which material suits his application best. And then we had a much better starting point when going into an aluminum mold.
We do have one question, Sebastian, which concerns the number of shots you can do with the simple mold without dissolving, and the material that is being asked for is specifically PA6 with a 30% glass filling.
Okay, so with the PA6 with 30, well, every material with glass filling, we shortly run into limitations. It will depend on the geometry of the part. How thin-walled, thick-walled is the part? Where's the injection point is critical to answer that question. And normally what we do if we have glass filled, we have a lost cavity, so we only do 1 shot. But we did have some applications where we did 5 shots, maybe up to 10 shots, depending on the geometry of the part. But again, here, we can also look at an option of a hybrid tool, which might be the better solution, especially if you're looking into maybe 20 or 30 parts.
So
to answer that question differently, because I know that's not the material that you requested, but if we use a standard PP, for example, we have done like shopping cart chips. We have done 200, 300 shots without any problem. With the same mold and a very good, very detailed quality. So that's really depending on the geometry of the part, the wall thickness of the part, and of course the injection molding material.
Are you getting a lot of cases like the one with the 5 materials? Because it seems to me like you don't have to select one material, one shrinkage profile from the get-go as you used to with conventional tooling. You have more freedom to actually examine alternatives. Is that something you see people do?
We see people doing that, and people should do that, because the material question might be difficult in your project. And if you carry that question for too long, things get too complicated and too expensive. So the earlier you can solve that problem, the earlier you can start with the real problems that you're going to have as soon as you decide the materials, maybe of how to eject the part, of how to actually work a serial tool with multi-cavities, things like that you want to address. If you haven't even chosen the material, you cannot even start answering these questions. So what it does is not only gives you the freedom to choose between these 5 kind of different materials, It also helps you to speed up the process a lot. And of course, in the long term, to save costs, because you have done a pre-evaluation of these materials, which you don't need to do afterwards again. And the best way would be that you start cutting steel and you don't need any design change or any rework.
That's a good point. Alexander actually has 3 questions. So I'm going to be asking them one at a time. The first one, I think you already mentioned en passant, but what accuracy can be achieved with printed molds slash dissolving molds?
So, well, first of all, we have the printing job. So what we do is we can print these kind of molds in a Z layer height of 25 micron. We have XY about 50 microns, something like that. We get a very good accuracy in the mold if we do multiple iterations. And then what we need to take into consideration is the shrinkage value of the material. So if we have materials that shrink a lot, let's say 1% or more, we would definitely need more iterations to achieve a tight tolerance. If we have materials that don't shrink that much, it is easier for us to compensate that in the printed tool. We do have parts where we can achieve tolerances in general without doing too many iterations of plus minus 0.1. We can go down to 0.05, but then we will in specific areas that are needed. And that's also how we try to look at the project. There might be an area of your focus, of the reason why you're testing these parts. So what you want to do is you want to be sure that you're only looking at these kind of areas. So what we do then is we look at that, maybe change a little the offset in whatever direction in the part itself, so at the end, after we dissolve the tool, have a good accuracy in the part.
And then the third question, and please be reminded to mute your microphones if you are on microphone. The third one is this combination good for achieving precious parts? And I guess those would be the high cost, complex stuff you were also talking about earlier.
Sorry, can you repeat just repeat the question, Lasse?
The third question that Alexander's asking is if this combination is good to achieve precious parts, and I'm guessing we're talking about those complex, high-value parts we have been examining in this webinar.
Yes. Well, again, it is a difference from project to project. It's really hard to judge that without seeing the part, without seeing the material that you're trying to use. So we would have to have a look at that. But as I said, we have injected all kinds of materials. We injected high-filled PPS. We injected PEEK. We injected PPS with almost 80% carbon-filled powder. So there are always options to inject these kind of materials. It is obviously the job gets more difficult doing that. And we need to have a closer look up front. We treat that as a real project. It's not like, and that's why we don't offer that kind of, so you cannot just upload your file and we will tell you, okay, we'll do that in 1 week. We need to talk to each other. We need to see that we meet the expectations, so the project is a success on both sides. And that is very important to understand before we can move on. We need to talk. We need to have that meeting up front. And then we can see if our expectations can match.
Excellent. So I think I don't have any more questions in the chat right now. Would leave 1 or 2 minutes. If you have anything you think we should cover that we haven't covered yet, please go ahead. And sorry about my voice. It's a little sore.
Yes, and so one thing that is also important, if you're thinking about maybe long-term or rather short-term implementing this technology to your portfolio and your company, it is very important that you understand that also building the molds or the way the molds are designed might differ from the way that you design traditional molds. And as we have these inserts here, these inserts have a certain size, and they have a certain size for a reason. So that's why so maybe one of you saw that the mold base, so the frame was 140 by 100, it was a lot bigger. But still, we would insert small inserts like that. We don't print it in 100 by 140. We do that for multiple reasons. First of all, it's a waste of the printing material that we dissolve afterwards anyway. The second thing is, it is key to the success of the injection molding process that we have the right size of the insert. So it cannot be too small and it cannot be too big. It has to be the right size to withstand the pressure, to make sure that the part afterwards is a success as well.
Excellent. So I think we will be slowly winding up this webinar. I just wanted to remind everybody that there is a Katina show coming up as the next thing. So do reach out to Sebastian, and Sebastian, if you plan to be there. I'll be circulating these slides, the video after this webinar has been concluded. And then I want to thank you all for participating today. I hope my voice will be better at the next webinar. And I look very much forward to seeing you all again at a later stage. Thanks a lot, everybody.